This video shows how to calculate the roots of unity. We will solve the equation z to the power of n equal to 1. This equation has n distinct solutions. Z equals 1 is always a solution, and z equals minus 1 is a solution when n is even. By rewriting the equation using the polar exponential form, we get the following equations. We can write z to the power of n and 1 in polar exponential form like this. Remember that k can be any integer. We can apply de Moivre's theorem to the left side of the equation to distribute the power of n. To solve, we equate the norms of each side to each other and do the same thing for the arguments. This means that the norm of z is equal to 1. Now we can look at the arguments of each side of the equation. The argument phi is equal to 2 times k times pi divided by n. Notice that when k equals 0, we also get phi equals 0, so z equals 1. When k over n is 1/2, then phi is pi, which means z equals minus 1. This can only happen if n is even. Therefore, there are n solutions for phi, larger than minus pi and smaller than or equal to pi. We will now take a look at an example and draw the solutions in an Argand diagram. We will start with the example of z to the power of 3 equals 1. We have the norm z equals 1 and the argument phi equals 2 times k times pi divided by 3. Phi must be greater than minus pi and less than or equal to pi. For k equals 0, we get z equals 1. For k equals 1, we get z equals e to the power of 2 pi over 3 times I. For k equals 2, we get z equals e to the power of 4 pi over 3 times I. We must subtract 2 pi, since this argument is greater than pi. We end up with e to the power of minus 2 pi over 3 times I. This result also could have been found by using k equal to minus 1. Finally, the solutions are z equals 1 or z equals e to the power of 2 pi over 3 times I, or z equals e to the power of minus 2 pi over 3 times I. Notice that the complex solutions form complex conjugates of each other. This concludes the explanation. Thanks for watching.